A large AI model can be hundreds of gigabytes in size and typically need a data center with rows of GPUs just to run. So how can we be in a position today where we can now run AI models on our laptops and our phone? Well, the answer to that is a fancy word called quantization. And it's the act of taking these large models and compacting them and squeezing them into a smaller file format size without losing accuracy in the process. And once you understand that, you'll understand how we're moving to an age where we're going to be able to use portable devices to run AI natively. Before we get into quantization in a bit more detail, let's just remind ourselves what a trained model is. See, a trained model is made up of many layers within a neural network, and each of those layers is effectively a grid where we can do multiplication of different weights. And each of these weights aren't storing facts, they're actually storing learned behavior. So think of it like your brain when you have neurons firing off. Each of those neurons are adjusted, multiplied, skewed in a certain way that they are activated based on certain inputs. And then they pass signals to other neurons to complete a flow and a chain of thought. See, for those weights, knowledge isn't stored as text. Each of those weights represent a number. It's all around probability. And though it's still hard to conceptualize this because neural networks have no sense of understanding sentences, it's all just based on probability of the next word and learning patterns over time. When you're exposed to so much information, we're talking billions of records of human history and sentences and structure, then you can train a model to predict what the next possible outcome would be and the most likely possible word. And then by training and stitching together those layers of a neural network, this is how we get the perceived perception of AI and human intelligence. So now we have all these layers, which are just matrix multiplication stored in a massive file. And that file was represented as either a .bin or a .tensor file. And each of the weights that we spoke about before are represented as really, really long numbers. And it's those really, really long numbers that allow us to build up such a good comprehension of all the different dynamics and language structures that we have in human language. So when you download a model from Hugging Face, what you're downloading is a file with billions of precise numbers that represent different layers within this neural network, which is our architecture. So how precise are all those measurements? Well, when we think around the weights, we typically store them as FP32, and that means floating point 32, where the 32 represents the number of bits. In reality, that means we can store values in the range of up to 4 billion. And that sounds like a huge number per weight. And it is. It gives us a tremendous amount of accuracy for firing neurons and signals that can be adjusted and tweaked based on the complexities of human language to come up with the right result that indeed Paris is the capital of France. But there's a cost of that, and the cost of that is storage. If we're storing each of our weights to the precision of bits, that means our output file, our .bin, our .tensor, which is the file format of an AI model, is actually massive in size. We're talking hundreds of gigabytes. So this is where quantization comes in. The beauty of quantization is we don't need to retrain our model from scratch. What we can do is actually look at all the outputs and all the weights from a trained model and scale them all together into a smaller file format, or rather into a smaller number format. The best way I like to think of it is imagine you're listening to a song on Spotify and you adjust the bit rate. If you have a lower bit rate, then the quality isn't going to be as good, but the song still sounds the same, aka the output is still similar. But if you had a higher quality bit rate, then you're going to get the precise tone of each of the instruments. Side by side, to the average person, they probably sound the same, but if you're an audiophile, you'll prefer that higher value output, and then you'd probably use a higher value AI model. But again, for typical scenarios that we're seeing in the everyday world, if we can quantize and reduce that bit rate and reduce the size, it's probably going to be good enough. So if we're not using FP32, what are we using? Well, the answer to that is integer 8. And that can have a value from -128 to 127, giving us a total range of 256 for our weights. Now that is dramatically smaller than the 4 billion that we had before, because every weight is scaled in a consistent way and we're changing the whole model scale at once. We are losing some accuracy, but the overall ability and cognition of the model remains remarkably the same. The way this clicked to me is thinking around quantization and AI training as a pinball machine. If we removed a few pins along the way, we would still most likely get to the same output. And that's all we're doing with quantization. We're reducing the accuracy slightly by removing some of the noise and information in there, but we're still able to get to the same output. And the reason we use ints and smaller numbers is going back to how model training works and neural networks work, is that because they are grids of multiplications, it's just easier to multiply numbers together that are smaller in size and that have less precision. It puts less strain on the GPU, and it means that we can now fundamentally train and run models on portable devices. We still need to use those rows of GPUs in data centers to initially train a model using that precision, but we can now use a simpler scaling method for running models that are pre-trained on our phone without losing too much accuracy. And quantization doesn't just make the calculations faster to be performed on a GPU, it also makes the file output smaller as well, because that .bin and that .tensor don't need to store all those weights to such a high precision. They can store it to a lower amount. So we're going to end the video here, and as a closing note, it's important to remember that for most people, quantization doesn't really matter, but what does matter is as scientists are able to further compress AI models to be able to run on your laptop and your phone, and possibly even your watch at some point, it's always a balancing act. You can't compress too much because then you lose accuracy, and that's going to make people trust AI output less. So I think over time we will see further compression, maybe using different file formats or using different values for the weights, but it's really impressive to see how far we've come in a short period of time. If this video made sense to you, please follow for more. Thank you for watching.